let's give you a quick review for previous class. In previous class, actually, we show you what is the thermal migration. Thermal migration, based on its name, is the mass transport under the temperature gradient. So we call it the thermal migration. And it is actually, we give you these examples demonstrate the effect of thermal migration. So in this solder bond, the composition is lead tin alloy. And before applying a temperature gradient, we can observe the tin mainly located at the bottom of the solder bond. And after thermal migration, after we apply a temperature gradient along or on this solder bond, then you find that the tin migrate from the low temperature toward to high temperature, which is against temperature gradient. This is a phenomena, is a typical phenomena. We call it a thermal migration because the migration of tin is due to the temperature gradient we apply on this solder bond or these materials. And in order to quantitatively demonstrate or understand the effect of this thermal migration, we use an example is we doped a dilute interstitial atoms in component 1, and we also apply a temperature gradient or thermal gradient on these materials. So after series deviation, we find that the interstitial atomic flux driven by this temperature gradient can be expressed like the first term is due to the concentration gradient or chemical potential gradient of this interstitial atom 1, which is minus diffusivity times the concentration gradient, and the second term is due to the temperature gradient we apply on this system, which is mobility, is diffusivity divided by kT mobility concentration, and the driving force here is a minus heat of transport temperature gradient divided by T. So the driving force is like this. Actually, this driving force is very similar with the temperature we learned at the end of the chapter 1. In that case, we also apply a temperature gradient on that, right? And if you remember, there's a two-chamber gas chamber, and one is with a higher temperature, the other one has a lower temperature, and the driving force for in that case is minus temperature gradient divided by T. So if the mass transport you observed in the solid material is driven by the temperature gradient, which is a thermal migration, then the driving force you just need to modify the heat of transport term, and the rest of part is is identical with what you learn in the end of chapter 1. Okay, so this is so you successfully can formulate the interstitial atomic flux driven by temperature gradient you apply on these materials. So what is the heat of transport here? In order to determine the value and the sign of the heat of transport, you can use this method shown in this slide. Is in the beginning, the concentration of these interstitial atoms is uniform along these materials, and after you apply a temperature gradient on these materials, and we find the concentration profile of these interstitial atoms becomes like this. So that imply or show us that there must atomic flux toward to right-handed side. So that can push some atoms moved toward to right-handed side. So that cause this kind of profile of interstitial atoms. And as we mentioned before, as long as there's a concentration variation happen along this material like this is high temperature, high concentration, low concentration, right? So spontaneous generate or raise the other atomic flux driven by the concentration gradient to counterbalance the flux driven by the temperature gradient. As long as these two flux reach steady state, which means the net flux equals to 0, then at that moment, then you can determine the value and sign of heat of transport based on what? As long as this concentration profile do not change over time, then you can use EPMA or SIMS material analysis system to get the concentration gradient along this material. And the temperature gradient is what you apply on this system. And the rest of part, this Boltzmann constant, temperature, and also the concentration of this interstitial atom, you know that, right? So you can easily get the heat of the value and sign of the heat of transport. But for example, like in this case, the concentration profile here is positive because the slope is like this. It's positive, negative, positive. So the upper portion is negative, and the temperature gradient we apply on this system can be either like this, can be positive. So negative divided by positive, so the heat of transport would be negative. And if you check the concentration profile between these two cases, then what you learn here is the atoms be pushed from left-handed side toward to right-handed side. If you take a look on the temperature point of view, then the atoms be pushed from low temperature toward to high temperature is against temperature gradient. So as long as you get the heat of transport is negative, that tell you the atoms, the direction of moving atoms, right? It's against the temperature gradient. It's be pushed from low temperature toward to high temperature. On the contrary, on the other hand, if the temperature gradient we apply on this material is negative, then the upper portion is negative divided by negative, then the heat of transport will be positive. Positive tell you what? The atoms be pushed from high temperature toward to low temperature, then so that will result this kind of profile. So it's high temperature be pushed toward to low temperature is the heat of transport is positive, and it just tell you that what the atoms be pushed along the temperature gradient because it's be pushed from high temperature toward low temperature. So the sign of heat of transport can tell you that the directions of moving atoms driven by the temperature gradient, right? So this is a similar concept what you learn from the beta in EM, electron migration, right? The sign of the beta also tell you the direction of the moving atoms driven by electrons flow or the electrical field. Okay, so in this slide we know the sign of the heat of transport is quite important. And next, because the heat of transport, this term actually is a little bit new to us. So this slide is going to explain more information to you. What is the heat of transport? So as we mentioned in previous slide here, the unit, yes, the heat of transport is related to what? Based on this deviation, you know the heat of transport is related to intrinsic material property, right? Because its coupling coefficient divided by direct coefficient is definitely related to intrinsic material property. The unit of heat of transport is what? Have any idea? If you check the unit, probably it's very difficult to you to figure out the unit of heat of transport from this term. But probably you can check this. The partial atomic entropy, the unit for this is the joule per K, right? Times K. So here the unit will be joule. So the heat of transfer, the unit for heat of transfer is joule, is the energy unit. Besides that is, then let's give you examples, try to understand what is the heat of transport. So now we can consider we have a material 1 is a long bar, and we put this and we find that material 1 diffuse. I mean, there's a diffusion happens in material 1 when at constant temperature. That means isothermally. That means at the constant temperature. And because in this system there are two possible driving forces. The first one would be, or only one driving force is diffusion happens and at a constant temperature. So if I try to write down the atomic flux and heat flow, the atomic flux is directly driven by minus chemical potential gradient times the direct coefficient, and plus what? Maybe some people will call that driven by temperature gradient, but at this moment it's isothermal at constant temperature, so we only have this term because the thermal driving force is equals to 0. And you also can formulate the heat flux J capital Q is directly driven by temperature gradient, and that term is 0. And you also the heat flux also driven by chemical potential gradient minus chemical potential gradient and times the coupling term, right? And based on these two equations, both of these have a minus chemical potential gradient. So the atomic flux and the heat flux and atomic flux have this kind of relationship. The heat flux can be expressed like the coupling coefficient divided by direct coefficient times the atomic flux. And based on previous slide, this term is equals to heat of transport plus Ts 1 bar. So we substitute this term, use heat of transport plus Ts 1 bar and times the J1 together. So the heat flux flow through this material 1 or flow through this long bar equals to what? Equals to the first term can be divided into two terms. The first term is the absolute temperature times the atomic flux times the partial atomic entropy. So these terms you can consider as what is a flux of entropy, right? Because this is entropy, partial atomic entropy times the numbers of diffusing atoms passing through a specific area per unit time. So you can consider the numbers of atoms times the entropy of atom is a total entropy, right? So you can consider and also the unit is per unit time per unit area, so you can consider a flux of entropy, right? And plus, so this term is the heat flux is due to the heat flux contribute from the entropy flux, and also plus the term. This term is related to what? This term is the atomic flux times the heat of transport. So the heat of transport is the coupling term between the atomic flux and the heat flow. So this slides demonstrate that even you put a material at constant temperature, and this material, if there's a diffusion happens in these materials, and there must exist a heat flow pass through these materials. And this heat flow is due to or accompanied by this diffusion atomic flux. So it's due to the flux of entropy. So let tell you that diffusion process is accompanied or associated with the increase of entropy. So some people call it is a flux of entropy. And plus the other term is the atomic flux also have a coupling coefficient with the heat flux, and this coupling term we call it is heat of transport. So heat of transport is a coupling term between the heat flux and atomic flux, and also, as you know, this term definitely is related to intrinsic material property, because for different materials, the heat flux induced by atomic flux definitely difference, right? Okay, so next slide is going to focus on the sign of heat of transport, and in this case we just copy the atomic flux driven by the thermal migration, and you got this equation, right? We copy this from where? Is from here. Okay. This term directly driven by temperature gradient. Okay. So based on this, but here we give you a negative temperature gradient. So this is negative, so become positive. So if the heat of transport is positive and positive, so the atomic flux will be positive. And the positive in this case will be toward to right-handed side. So it's like this. So the atomic flux is pushed, the atom is going to be pushed from high temperature toward to low temperature. So that's what we learned from previous slide because the atoms be pushed from high temperature toward to low temperature is along the temperature gradient, and at least conditions the heat of transport must be positive. And on the contrary, if the heat of transport is negative, and this is negative, and negative, so the atomic flux driven by temperature gradient is negative. In this case, negative is toward to left-handed side. That implying that the atoms be pushed against the temperature gradient is from low temperature toward to high temperature, right? Okay, so I draw some possible cases here. In the beginning, yes, you have the uniform in the interstitial atoms along your materials, and you can apply two different directions of temperature gradient. This one is negative, and this one is positive, and based on the sign of the heat of transport, then you have in this case you can divide it to different two conditions, right? This is heat of transport is negative, so negative, that means against the temperature gradient, so you push these atoms toward to this direction, so the profile will become here like this. And the heat of transport is positive, that means the atoms be pushed from high temperature toward to low temperature is like this. You push the atom toward to right-handed side, so that you can find more atoms accumulate at right-handed side will become like this profile. Okay, so the same idea, okay, same concept we apply here. So you can try to draw this by yourself, then I believe you have more feelings of more idea about how to predict the concentration profile of interstitial atom driven by the temperature gradient. Okay, So I give you a summary here. For thermal migration, the mass transport driven by temperature gradient, the driving force here, we use the heat of transport to modify the thermal driving force. And due to the driving force be modified, so we can reformulate the atomic flux of mobility, concentration, and modified driving force here. So compare the thermal migration and electron migration, we know the beta, the effective charge of beta, and heat of transport, these two values, some people call it is like these two parameters can well describe the direction of moving atoms be applied on either electron field or electrons flow or the thermal gradient. Okay, and these two parameters also tell you the most important thing is the value and the sign of these two parameters can well describe the directions and the magnitude of the directions and the velocity of diffusing atoms be driven by either electrons flow or thermal temperature gradient. Okay, so this is just for this slide. We talk about this before is the network constraint. We can use this when our system only have when the changes in one component lead to changes in the other component in our system, then we can use the network constraint. So, for example, like in pure metal materials, the numbers of atoms and the changes with vacancy, the numbers of vacancy. So you can use this to formulate the driving force of pure materials. So before we end the thermal migration part, we are going to give you the other examples, which we call vacancy mediated thermal migration. So what is a vacancy mediated thermal migration? So vacancy mediated here means like the diffusion process. Diffusion mechanism in these materials is vacancy dominant. So let's give you an example here. So I grab a slice from chapter 4, and in this case, this is one kind of atomic diffusion mechanism we call a vacancy mechanism, vacancy mediated mechanism. This is the black and blue circles represent the atoms, and the diffusing atom now is this blue circle atoms is it is at the substitutional site, and it will exchange with the neighboring vacancy through the atomic jumping. So this diffusion dominated by this kind of exchange with surrounding or neighboring vacancy. So this vacancy mediated diffusion depends on what the vacancy concentration and also the atomic migration energy. So in this kind of materials, the vacancy number or vacancy concentration is quite important because this vacancy concentration will dominate how fast this diffusion happens. So this kind of material, we call it is a vacancy mediated materials. And if you apply thermal migration on this kind of material, so besides the atomic flux, what we learn here, let's the other possible driving force here. Possible force to effective the atomic flux, which is the vacancy concentration. Because as we know, the vacancy concentration or equilibrium vacancy concentration is proportional to the Arrhenius relationship, which is exponential minus vacancy formation energy divided by kT. In this case, if the temperature gradient, we know that the vacancy concentration is highly dependent with the temperature we apply on these materials. So if in this case we apply a temperature gradient along this material, and the gradient the gradient would be negative like this. And if you try to plot the vacancy concentration as a function of location, and at higher temperature you got the higher CV, highest vacancy concentration. For lower temperature you got the lower CV, right? And this kind of variation in vacancy concentration will drive a vacancy flux toward right-handed side. And as you know, if you have the vacancy flux to right-handed side, that tell you that there must atomic flux toward to left-handed side, right? So the vacancy flux is along the temperature gradient, and this kind of flux would tell you that there's an atomic flux against the temperature gradient. And this atomic flux is due to the vacancy flux. It's nothing related to the thermal migration we talked in previous case. So you need to modify the atomic flux in this kind of cases through consider additional driving force, which is consider additional reasons, which is the vacancy the difference of the or variation of vacancy concentration. So there's extra term. It's a vacancy formation energy, and this we need to end it here to modify this atomic flux in this vacancy mediated materials. So if you consider this vacancy gradient effect, then you can divide it into two cases by the sign of the heat of transport. For example, if in this material the heat of transport is negative, that means the atoms, the atoms be pushed from low temperature toward to high temperature, so there must atomic flux toward to left-handed side driven by temperature gradient, right? And this term is in the same direction of this atomic flux driven by vacancy flux. So if you sum up this result, so you got the higher atomic flux. But if the heat of transport of this material is positive, that means there's an atomic flux toward to right-handed side to push the atom from high temperature toward to low temperature, right? And this direction is totally opposite direction with this atomic flux driven by vacancy gradient. So that will cause the smaller atomic flux, because you sum up these two terms, and you will find the smaller atomic flux toward to right-handed side. So here, if in your material, if your material is vacancy mediated material, the diffusion process is vacancy mediated, and you apply a temperature gradient on this material, in addition to consider the thermal migration itself, that means the sign of the heat of transport, you also need to consider other parameters. Here is the vacancy the concentration of vacancy. So you need to modify the atomic flux by ending this term. Probably some people will ask why the vacancy formation, the modified term is put here instead of put here. So as we mentioned before, there can be two possible reasons. Based on this published results, he find that by doing experiments, he found that the vacancy, this term should be modified in this the heat of transport. And the reason is the unit for heat of transport is the energy term, and the vacancy formation energy also is the energy term. So they'll be suitable to end it here. And also in this paper, the scientists, by doing experiments, the scientists confirm the results and propose the vacancy gradient effect should be put here to modify the atomic flux. Okay, so probably you can consider that, for example, like have a look here. If the heat of transport is negative, the negative minus a positive term, so it's more negative, right? So the summation results is the value is get more negative, the value is get larger. And if the heat of transport is positive minus a positive term, the value should be smaller than it was, right? So get smaller. So no matter it's in case 1 or case 2, so the results of atomic flux, the magnitude of atomic flux is reasonable. Okay, so as long as your materials is vacancy mediated materials, then you apply the thermal gradient on it. You need to consider two parameters. The first one is thermal migration. The second one is the vacancy gradient effect. Okay. So we already finished the thermal migration induced mass transport, and we divide it in two categories. The first one is we dope the interstitial atoms in your interesting material, then you apply a thermal gradient or temperature gradient on it. Then we find the atomic flux of this interstitial atom can due to the concentration gradient and also the thermal driving force. And the second case is we call a vacancy mediated materials. In this case, in addition to consider the thermal migration effect, you need to consider the vacancy gradient effect and put here to modify the atomic flux. Okay, so I give you a summary here of thermal migration. Thermal migration is a close effect between the diffusing species and the heat flow. And as we mentioned, and there's a parameter we call a heat of transport, which will describe or characterize the thermal migration effect. And the sign of heat of transport determines the direction of diffusing or moving atoms driven by this thermal or temperature gradient. And this is the two important equations. The first one is the heat flux. It can be contributed from the entropy flux and the atomic flux. And the heat of transport here is the cross reaction, the coupling term between the atomic flux and the heat flux, which we call the heat of transport. And in this case, by using this equation, you can have an idea when you apply the temperature gradient, and no matter then you can, and you can observe the atomic flux and which can give you some information about the size of heat of transport. Okay, so next slide is some kind of case study. As we mentioned in the solder bond, this picture actually is what we mentioned in previous slides, the solder bond, and upper portion is the silicon die, or usually people will put some transistor on the silicon chip side, and the bottom part is a copper plate for heat dissipation. So usually the solder bond can help us to lead the current or signal in and out. So in real case, how can we determine the heat of transport, the size of heat of transport in this kind of real cases? As you know, usually the solder bond suffer two driving force in the meantime, right? The first one is temperature gradient, what we talked about before. And actually, the solder bond also suffer the second driving force is a current passing through the solder bond. So on each solder bond, it always suffer two driving forces. So in this kind of real case, can we realize or determine the heat of transport of this solder bond? How can we do that? So here, in this case, this material is tin, pure tin. Then after 16 hours, the current density is 1.3 times 10 to 4 m per centimeter square. How can we determine the size of the heat of transport? So this is a question 1 and 2, right? The first one, you need to determine whether the TM happens in your solder bond. And second, if this TM happens, can you determine the heat of transport is positive or negative? So here we provided you some following methods. Is you can directly switch the direction of electrons flow and analyze whether there's a void form in your solder bond and at which kind of locations, so you can have some ideas about whether the TM happens, and also determine the size of the heat of transport. And let me explain why. If you switch the direction of electron flow, as we know, as long as you apply the electrons flow, this electrons flow will push the atoms toward to the same direction of electrons flow, right? So in this case, the tin be pushed to the bottom. And in this case, because we switch the direction of tin or electron, switch the direction of electrons, so there's the atomic flux driven by EM toward to upper direction. And next, in addition to this EM effect, this solder bond also suffer the TM. Why suffer the TM? Because you can observe what we have here is, you can observe a larger void form in this case, but smaller void form in this case. So in this system, definitely coexist other driving force. So I will propose probably is suffer the TM, but the direction of TM we need to determine that. So how to determine that? The first of all, you need to determine which side is higher with a higher temperature and which side has a lower temperature. As we mentioned before, silicon substrate side usually you put transistor on it, right? So the line width usually is smaller. than that on the copper plate. So the light width is smaller, so that means the current density is higher at this side compared to at this side. So higher current density based on the Ohm's law. This side usually has a higher temperature compared to this side. So no, this is nothing related to the direction of electrons flow, right? Because the key point is the light width at this side is smaller than this side, so that will cause the higher current density here at this side compared to this side. So this side, secant side, always with a higher temperature, and so you will get the high temperature here and low temperature here, and consider this, you observe a large void and this small void. So I can propose the direction of thermal migration here. Because the atomic flux is toward to bottom, and this is larger, right? So I can propose the atomic flux driven by thermal migration is toward to bottom. Because bottom, so you got the larger void, and if it's bottom, so these two atomic flux have chance to counterbalance each other, so that will result a smaller void. So based on this propose, we know the atomic flux of tin driven by thermal migration is from high temperature toward to low temperature. So this is along the temperature gradient. So I believe the heat of transport in this case is positive. So this is how we this is the way we get the sign, have some idea of the sign of the heat of transport. This is a real case because probably if you checking literature, some people will use the like this way. This main method, which we show in our slides, this as long as it reaches quasi steady state, then you by investigate the concentration gradient and the temperature gradient, you know the sign of the heat of transport, right? But as we know, how to define the quasi steady state in real case, usually we just propose a reasonable time period, probably is 2 days or 7 days, and we find all the profiles not change with time, something like that. We make some assumptions, something like that, then you can have idea. At that moment, you get the sign and value of the heat of transport by, right? But in semiconductor, the research in semiconductor industry, they usually use this kind of ways to have some idea about the heat, the direction, or the value, the sign and value of the heat of transport. Because this kind of test is real test. Because this solder bond is in the meantime, it will suffer 2 driving force. In this kind of test, you can have the value of heat of transport, or the sign of the heat of transport is more close to reality, the real value of this material, real value of heat of transport of this solder bond. Okay. And here I also provided you some other ways to measure the heat of transport. Some people, instead of using this kind of test, some people also try to dig some micro holes on the solder bump by using laser. So after diffusion, you can compare that the moving direction of these micro poles, then you can have some idea about the direction of atomic flux. This if you check a literature, some people do that to have some idea about the direction of atomic flux, which you are interested in. But this case, this kind of method is normally performed on the package. You want to know the reliability of this solder bond, or not only the reliability, also how good of the solder bond is. So you will run this kind of reliability test up to 16 hours at this kind of current density. So you can have more simulate the real conditions which the solder bond were suffered in the microchip. So I'll give you a summary of the electron migration and thermal migration. The electron migration is the cross effect between the diffusing species and electrons flow. And the parameter, which is the beta called effective charge, can give you some idea about the direction of diffusing atoms driven by this electrons flow. And the thermal migration also is a cross effect between the diffusing species and heat flow. And we use the parameter heat of transport to have idea about the moving directions of these diffusing atoms driven by temperature gradient. And by the way, are there any possible driving force can counterbalance the atomic flux driven by temperature or temperature gradient? Yes. The concentration gradient is a possible driving force to counterbalance this flux, and the other would be the vacancy flux have some possible, also can have chance to counterbalance the atomic flux driven by thermal migration. Okay.